So I'm making this video here to give you guys an example here of how to analyze an oblique type of impact here. So this is number 93 here in chapter 15. And the thing to pay attention to right now is this very first picture. So I got two objects, mass B, mass A. Mass B moving right at 8 meters per second, mass A moving left at 10 meters per second. And they impact in such a way that the normal here makes this 3, 4, 5 triangle. So these can be very important directions for these impacts, the normal and the tangential direction. So they're drawn in and labeled in the picture. So the second picture now basically clone the first picture, and the second one's showing the impulses. And it's important to note that the impulse on mass B is coming from mass A, and the impulse on mass A is coming from mass B. And also notice there are no external impulses acting on this system. Now that's kind of nice because that allows us to write momentum conservation in all directions as far as the system is concerned. Also notice there are no impulses acting on either mass in the tangential direction. So what that allows us to do is write a momentum equation for each individual mass along the tangential direction. All right, third picture. So the third picture is just after impact. Would have been nice if I could have got a little space maybe in there, but so mass A's velocity vector is likely something like this, and you'll notice I've broken it into components in the tangential direction and the normal direction. So that's what I mean by VA2 tangential, VA2 normal. Mass B's velocity vector, likely something like this, broken into components, VB2 tangential, VB2 normal. And again, the reason for looking at the tangential and normal components is because we know we're going to be dealing with that coefficient of restitution. So now it's just a matter of starting to write equations here. So the easy guys to get are these guys, the tangential velocity components. And the way we can do that is we can write an equation here. I'm going to go ahead and write an equation here for mass B, and that equation is going to be conservation of momentum for mass B, and I'm going to go ahead and call this the positive direction. So looking at mass B here, mass B I believe is 10 kilograms times 8 meters per second. Now I want the component of that momentum that's in the tangential direction. So you'll notice here's an angle theta, and you'll notice it's the same as this little angle right here. So that's going to be mv sine theta. And looking at this picture, sine theta is 4/5. That has to equal the tangential component of the momentum vector in this picture. So that's going to be mass B, 10 kilograms, times VB2 tangential. And if we solve that, we can solve that for VB2 tangential, and we get, let's see, what do we get out of that here? I get 6.4 meters per second when I work that out. And direction down and right as shown. So there's one equation we can write for mass B. Now I'm going to write a similar equation for mass A. I guess I'll move that over here. So conservation of momentum for mass A. Again, down and right positive. So for mass A, let's see, mass A's momentum, we're going to have 15 kilograms times 10 meters per second times, again, the sine of the angle theta. Now this angle theta and this angle are the same, so that's going to be times 4/5, and that's going to equal the momentum in this picture. Now I've got down and right positive. This velocity vector is up and left, so that's going to be minus 15 kilograms times VA2 tangential. And if we solve that for VA2 tangential, let's see, we get 8 meters per second. Okay. Whoops. You know what? I think I was glancing there at... Seems like I missed a minus sign somewhere. Whoops. Oh, right here. Okay, so if we apply conservation of momentum, and I call down and right positive, and we take a look at this initial velocity vector, this guy's tangential component would be this way, and I've got down and right positive, this guy's up and left, so there's a minus sign right there that I missed. So when we solve this for VA2 tangential, we get positive 8 meters per second. The positive sign is indicating that this is in the correct direction. Alright, so I'm going to take a moment here now. We've got VB2 tangential and VA2 tangential. I'm going to take a moment, pause this, clean this up, and then go after the normal components. Alright, I'm back here. So now let's deal with the coefficient of restitution. So the coefficient of restitution is VB2 minus VA2 over VA1 minus VB1. Now, when we went through this in class, you know, we had picked a particle to call A and a particle to call B. The good news is it doesn't really matter which one you call A and B. If you reverse the top, you're going to end up just reversing the bottom, and all it does is flip the minus signs on both. So I went ahead and just did this. So we're going to have 0.8 equals. Now, here's an important part about coefficient of restitution. It only applies in the normal direction. So when we apply this, these are going to be the components in the normal direction. So that's going to be, oh, and I should point out that I'm calling down and left positive when I'm writing this out. So that's going to be VB2n minus VA2n over VA1n minus VB1n. So VA1n I got over here. So here's VA1. We'd have to multiply that by the cosine of this angle, which is 3/5. So that's why it's 10 times 3/5. Now the next term is minus VB1, the n direction. So here's VB1. The component of this that's along the n direction here would be VB1 cosine theta, which is going to be VB1 times 3/5. But notice this points up and right, and I'm calling down and left positive. So VA1n minus VB1n is 10 times 3/5 minus a minus 8 times 3/5, and hence the plus sign. So when we rearrange this equation a little bit, we get 8.64 is equal to VB2n minus VA2n. What I'm going to do here is kind of store this equation and get rid of this other stuff here. So, give me a moment here. Okay, so we have an equation here for VB2n and VA2n from the coefficient of restitution. We can get another equation for VB2n and VA2n by applying momentum conservation in the n direction. So if we do that, looking at this picture here, so conservation of momentum, n direction, calling up and right positive n direction. And again, this equation is going to be for the entire system. So the component of this guy's momentum that's in the x direction is going to be 10 times 8 times cosine theta. Looking right up here though, cosine theta would be 3/5. Then this guy's momentum is, let's see, mass 15 kilograms times velocity 10 meters per second times the cosine of this angle, again same angle as this, so times another 3/5, except this guy's momentum points down and left instead of up and right, so that's going to be minus. I should put a little NCU here, note consistent units, since I'm not bothering to put them in. So this represents the net momentum in this picture along this axis right here, calling up and right positive. And that has to equal net momentum over here, calling up and right positive. So that's going to be minus 15 VA2N. That's this guy's momentum along the n direction, minus because it's this velocity vector here if this component points down and left instead of up and right. And then this guy's momentum component in the n direction, also minus, and I think that was 10 kilograms times VB2N. So we have a second equation here now for the VB2s. Well, for VB2N and VA2N. And let's see if we clean that equation up a little bit. I think that simplifies to 42 is equal to 15 VA2N plus 10 VB2N. And there's equation 2. If we go ahead and do a simultaneous system here, solving equations 1 and 2, I work this out. Give me a moment here and I'll take a look at that. Okay, I'm back here and I cleaned it up a little bit and just kind of wrote the results down. So solving that simultaneous system of equations for VB2N and VA2N, I got 6.86 meter per second for VB2N and negative 1.78 meter per second for VA2N, which is no big deal at all. Minus sign is just indicating that this velocity vector is opposite direction shown, meaning that this thing should be up and right instead of down and left. Now, before we had gotten 6.4 meter per second for VB2 tangential and 8 meter per second for VA2 tangential. The question actually says to find the speed of each after impact. So applying Pythagorean theorem to these, I get 9.4 meter per second for VB2 and 8.2 meter per second for VA2. It does not actually ask for directions, but we can find them easy enough because now we know each component in these triangles. So for example, the tangent of this angle would equal VA2N over VA2T. Keep in mind that that VA2N was a negative number. That just means that that angle is going to be like up into this quadrant. And the tangent of the angle alpha is going to equal VB2N over VB2 tangential. So these things are kind of a pain. They're not the easiest problems in the world, but the key to these is this picture right here, really. When you're analyzing any impact, make sure you draw a picture showing all relevant impulses during the impact time frame. Some of these, there will be no external impulses, in which case you can apply momentum conservation in any direction you want. If there are no external impulses, some of them will have external impulses, in which case you have to be careful about which directions you apply momentum conservation. In this particular problem, we can apply momentum conservation along this axis for each mass, or for the system, because these are internal impulses. And we can apply momentum conservation along this axis to each mass individually, because there are no impulses acting in this direction in this problem. So anyway, hope this helps, and I'll start working on another one for you.